what I'm going to talk about today is quite a controversial topic these days, sadly, I guess, I don't know. But I'll be talking about the study that I did on the async code reviews, and it was a pretty extensive study that spanned, I think, already 2 years of work through which I analyzed more than 40,000 pull requests. And I had a couple of interesting systemic insights. Some of those I expected to see, I had a hunch for those, but some of those were kind of unexpected. So I would like to share my journey with you. So my name is Dragan Stepanovic. I work as a senior principal engineer at a company called Throughput, which is a delivery hero group. And things that preoccupied most of my career have been these 4 topics: extreme programming, theory of constraints, lean, and systems thinking. And these years, I'm trying to connect the dots between these fields, and there's a lot of overlap, really interesting overlap that I found. And this study is also one of the byproducts of that. I rant on social networks, and there's also one terrifying fact about me, terrifying especially for Italians. So I put mayo on pizza for some reason. That's the reaction I expected to see also, so yeah. But yeah, it started at one point, and yeah, now I cannot get rid of it. I would like to frame today's talk in the just sharing principle. So I'm not saying that the problems that I have are the problems that you have. I'm not saying that even if you have this problem, this is the biggest problem that you have in your teams or organizations. I'm here just to share the journey that I had. So, not sure how many people have heard for this quote, nobody ever got fired for buying IBM. And I wasn't in the industry at that time, but what I heard during the 80s that IBM had a huge market share as a vendor. And if you were working as one of the folks in the procurement departments, you had a hard time not buying IBM. If you wanted to go with some other vendor, you had to answer lots of questions. So going with the crowd kind of serves as a strategy to minimize the downside risk, so to say. If something goes wrong, hey, yeah, it's IBM, who could have known? And when I think about this quote and I think about the ways that we work, I usually also think about the workflow that I call PR-based async code reviews. And I try to visualize it here. And we'll quickly go through it. And I'm not sure how many of you also are working the same way. That's kind of interesting thing that I would like to know. But what we see here is that we have 2 developers, Emma and Luca. And let's say it's the start of iteration. They're working individually. So Emma pulls in ticket number 1. Luca pulls in ticket number 2. And Emma, once she's finished with the implementation of the feature, figures out, okay, I think I would need feedback from my peers. So she invites Luca for a review by raising a pull request. But Luca is busy with ticket number 2. And there are a bunch of other things that are going on, like meetings, stand-ups, refinements, reviewing other PRs, breaks, checking email, checking Slack, etc. So he's not able to respond immediately. Now, Emma, wanting to be a good engineer, she doesn't want to twiddle her thumbs while she's blocked or waiting. So she pulls in ticket number 3. Okay. At one point, she figures out, seems like Luca is not responding, so let me try to remind him again. So she does so. Luca at one point comes around and responds, asks for some changes. They go back and forth a couple of times, and eventually they figure out, okay, now we are satisfied with the solution, so let's approve and merge the PR. So this is the PR-based async code review process, and I'm kind of curious how many people tend to do this in their teams or in their organizations. Okay, cool. So I usually get asked to consult and mentor and coach teams when it comes to the ways of working. And my guiding principle is meet people where they are. So it doesn't matter where you're currently at. What matters is the trend line or where we're heading. And there's a certain share of managers and developers that wanted to understand where do they currently stand when it comes to the way of working, so they can also understand what is the, let's say, next desirable state that we can move towards. And this was the reason for me to try to understand a bit more of the data behind all of this process. So throughout the course of the study, I analyzed more than 40,000 pull requests, as I mentioned, and these were from the teams that were typical product development teams, so no open source. Okay, and this model is, as we know, kind of adopted in the product development teams from the open source community for some reason. And the things that I was curious to see were, at the start, engagement, wait time, and size. Now, when it comes to the engagement, the things that led me to try to understand what's going on and why was it interesting to me, it was this analogy that I had in my head that when I have a call with someone or the phone and there's a delay in communication, the conversation tends to die off pretty quickly. So we converge even before we want to do so because of the delays in the communication. And I was curious to see like how does this systemic delay affect the engagement that I get to see on the PRs. Now, other thing that is also important when it comes to the PRs is that the feedback is usually provided in a written form, right? So that's pretty much different than when you have face-to-face conversation, and the bandwidth that you're using as a medium conversation is pretty narrow, right? And we know it also from the onset of pandemic that written communication can also be misunderstood a lot, right? So this is the thing, this is the reason why I call this kind of way of working high latency, low throughput feedback, or when it comes to engagement at least. And let's go into data. So this is a data sample, I think 500 merged pull requests. And the things that I'm going to talk about today were present in all of the data sets that I analyzed for the teams that were doing async code reviews. And here on the x-axis, we can see the size in lines of code. On the y-axis, we can see the engagement. Now, I went with a simple lines of code as when it comes to the size of the pull request, and also as a proxy metrics for how much time did we invest in this. The PRs that have been worked shorter amount of time, but they produced a lot of the code, let's say updating a library, etc., were filtered out from the study. And what I found that as an approximation size was pretty good one. There's also this thing that different people or use different things to figure out the complexity of the work. You know, some people look at just at the lines of code added. Some people look at the number of files changed, etc. But for this study, the size as the lines of code was enough. And then on the y-axis, we can see the engagement, which is number. The way that I went about it is number of non-trivial comments that you get to see in the code. So non-trivial comment is a comment that is not trivial. And the trivial comment is a comment, this is a silly, sounds as a silly definition, but a comment that has 4 or less words in it. So these comments were filtered out as trivials. The reason for that was that I got to see a lots of looks good to me, thumbs up, +1, LGTMs, etc. And those are the feedback that doesn't really serve the other side when it comes to the valuable feedback, right? So what can we see from this catapult? Not much. Most of the PRs are less than 500 lines of code and have less than 10 non-trivial comments, but that got me thinking. If I spend a lot of time and I get, let's say, 2 comments on the PR of 1,000 lines of code, versus when I spend, let's say, half an hour and I produce 50 lines of code and I get 2 comments, it's kind of a different thing. The amount of feedback, at least when it comes to the number of non-trivial comments, is different. I'm not saying anything about the quality of the comments, but just the fact that we have a different amount of non-trivial comments depending on the size was something that got me into thinking how would it look like if we were to plot the engagement per size on the y-axis, so to normalize the y-axis by the size. And that was the interesting part. So this also kind of matched my experience. I'm pretty sure it matches lots of your experience. And the way that I see it is that as we increase the size of the pull request, the engagement per size tends to go down, right? And the reasons for that are kind of if you get 1,000 lines of code pull request, the thing has already been done, right? There's not much you can do about it at that point in time. It's very difficult to course correct and steer, right? Plus, there's, from the other side, from the author's perspective, the fact that you invested a lot of time and now you have to change. If you went astray, and you usually go astray, you need to change a lot of the code. That's very, very psychologically taxing, so to say, or emotionally, right? So the sunk cost fallacy also kicks in. But for me, what was important here was that we are using code reviews to embed or building quality through human judgment, right? And if that's the thing, then if we're not getting feedback, then we're also not able to build the quality. Okay. So for the bigger PRs, it's the amount of feedback that we're getting is kind of getting lower. And I'm not saying anything about the left-hand side. So if you have, I'm not saying that you have a lot of feedback that has to imply quality, right? That's a different thing. Depends really on the seniority of people, the type of the knowledge that they have, domain experience, etc., right? But I'm saying if you're using this process to build the quality and we're not getting feedback, then we're also not getting quality. Okay. Never had a huge PR that didn't look good to me. So apparently all of the PRs that are big look good to us. And I'm kind of curious how many people have experienced this thing. 10 lines of code, 10 issues, 500 lines of code looks fine, right? And I think those are these kind of forces, systemic forces that start kicking in, very difficult to course correct at that time. The thing has already been done. So the other day I also ran into this video, and this is what trying to build the quality in with big PRs looks like. Just yours kind of trying to do something, but yeah. So going into the wait time, wait time was the part where I had lots of interesting systemic insight and some of the surprises that I didn't expect. So if we go back to the visual and we focus on ticket number 1 here, and just pull up its life cycle or its lead time, what we can see is that there's a portion of time where we're working on this item effectively, meaning Emma coding or Luca reviewing, etc. But there's a portion of its lead time where it's just sitting there in a queue waiting for someone's attention. And this is the definition of a wait time. And this is the metric that also comes from Lean. You can hear it also as queue time. So I was trying to figure out, okay, the approximation for measuring the wait time. And the way that I went about it, again, this is approximation, is good in some cases it's not good enough. And the way that I see a typical product development flow, so to say, is that we as engineers start working on something, and at one point we think we're done, so we raise a pull request and then we invite other people for feedback. And this is when the time, wait time starts ticking. Okay. So if I get to see a lot of engagement after raising a pull request or lots of follow-up commits, that tells me that this approximation is not good enough. Okay. So some of the results. One of the data sets, number of PRs analyzed, so these are merged PRs. For this team, it took them 6 months to push 500 pull requests through their system of work. So since the start of the first PR until the end of the last PR, it was 6 months. And what was interesting to see is that cumulative wait time, so wait time for all of the PRs summed up was close to 28 months, which is a lot. And I'm not saying that this particular metric is particularly precise, but even if it's half precise, so to say, it's already a really good conversation starter about the way that we work. Okay. And why I find this really important, if we extend this point, is that we deliver value to our customers by changing the code. And the code that we change is valuable to some stakeholders, hopefully valuable, right? And if we're saying that we're not even able to deliver these changes to the code, of the code to the customers when we want, meaning that they're stuck in the system of work for a longer time, we're also potentially delaying delivery of value to our customers, right? So that's why, for me, it's really important to understand how much of a wait time do we have in the system. The reason why this is important is we want to experiment faster, we want to deliver sooner in order to understand if we're on the right path or we're on the wrong path. And one analogy that I had in my head is this game that we played when we were kids, hot and cold game. So one person hides an item, the other one looks for it. And the person that hid the item gives feedback. And if you're closer to the item, the temperature is going up, and vice versa. And let's say that you have two teams. So one team, they're getting feedback after 1 minute, and the other team is getting feedback after 1 second. On which of these two teams would you bet that they're going to find an item sooner? Pretty much on the second one, right? And this is why the cadence is so important, right? So going into the scatter plot for wait time, so this is wait time by size. And there's, again, not much to see here. Most of the PRs have less than 200 hours of wait time. But then it also got me thinking. So if I work, let's say, on a PR for a week and I produce 1,000 lines of code, and then I wait 2 days for a review, it's not the same as when I invest, let's say, half an hour of time, then I wait 2 days for a review. The relative cost of code review is very different. So what happens if we normalize the y-axis and we get to see wait time per size by size? Now the things start getting interesting. And this was also present in all of the data sets. So what happens is that as we reduce the size of the pull request, the wait time per size goes up exponentially. Okay. And the way that I understand it, or the way that I interpreted this, is that the cost of code review per size goes up exponentially as we reduce the size of the pull request. And that was a surprising thing for me, because when I get into teams and I see that they're doing a big pull request, I start asking myself, what's the reason behind that? So, and I advise to do smaller pull requests, and we want to have small pull requests. This is the lesson that we learned from Lean, from small batches. Small pull requests take less time to write. They also are quicker to review, less time to review. The time allocation from a reviewer is less, so it's easier to squeeze in into your schedule, right? As we saw, there's also higher engagement. They're less risky because less things get changed and deployed. And when something goes wrong, it's easier to troubleshoot. And they also positively contribute to all 4 DORA metrics. Okay. So we have a system where when we reduce the size of the pull request, the cost of code review per size goes up exponentially. And I bet that you also had a chance to experience this in some other scenarios. If you have a long-running test suite, let's say that it takes you 20 minutes to run a test suite, you're not going to run test suite after every line of code change. Why? Because it doesn't make any economic sense. Most of the time, you're just going to be sitting there waiting for the test to finish. So what the system is incentivizing us is to increase the amount of changes that we introduce to the system before running a test suite. So we're sliding back into the bigger batches, right? And that's the place of the spectrum where we don't want to be. And because of that, I really love this quote from Don Reinerson: while you may ignore economics, it won't ignore you. So be very careful about the economic incentives that you have in your systems of work. Another implication is try doing small changes and refactoring in this kind of environment. It's going to be very, very hard, right? Because the system is punishing us. And that's the reason why I think that the teams that have lower latency in communication tend to have higher code quality and healthier code bases, because they get to refactor when they want, not when it's not expensive. Okay. And pull request nitpicking. How many people here had the chance to encounter this? Like a syndrome or example? Yes. And I found it really interesting because I saw it in the teams that had a high latency. And why it's interesting to me is that, so the nitpicking is about reviewers asking for small changes, but it's perceived as a reviewer being nitpicky, okay? And I was curious to run a Google search on this topic, and guess what? Gazillion of articles on how to stop nitpicking in code reviews, why they're not good, etc. But for me, what's interesting that the peer nitpicking is not about peer nitpicking. If you have the same people working together, you're rarely going to see that there's a sense of nitpicking, because the cost of integrating changes is very low. When the cost of integrating changes is high, your request needs to be so important that it gets above this threshold of not being interpreted as nitpicky. Okay, so that's interesting thing to notice. So these LGTMs, nitpicking, are also byproducts, undesirable byproducts of a system of work that is system giving us feedback. Okay, and we need to listen to that. So, talking about the teams, doing async code reviews, and me trying to figure out how can we reduce the size of the pull request, and trying to make sense of it. And here is, I present this through a causal loop diagram, which is a tool from systems thinking. And there was a lot of talk about systems thinking in this conference, which is really great to hear. And just to give you a short crash course, so here we have two types of links. So you have a red one and a green one, and you have some labels. And these labels are variables. And if there is a link between variables, which is minus or red in this case, it means that when one variable goes up, the other one goes down, and vice versa. Okay. When there is a positive link, that means that they go in the same direction. So if one goes up, the other one goes up, and vice versa. And what was interesting is that when you start drawing these things, start connecting the dots, you might discover some feedback loops. Okay. So two types of feedback loops that are important is the reinforcing feedback loop, which is a snowball effect. The more of something you have, the more you have it. And the other one is the balancing feedback loop, which is a feedback loop that seeks a goal. So balancing feedback loop is, example, if you have a thermostat at home and you set it to 21 degrees, the system is going to work until it matches these 21 degrees and is going to stop at that point. If you open the door, outside is cold, it's going to work even harder until it achieves the goal that you asked it for. So me trying to make sense of why cannot we reduce the size of the pull request in async code reviews, or teams that are doing async code reviews, let's do a walkthrough. So if we reduce the size of the pull request, the motivation or incentive to review goes up, as we saw it also, which is a good thing. And then likeliness to review also goes up, which means that the time waiting for a review goes down from the author's perspective. As the time waiting for a review goes down, the perceived cost of code review per line of code from the author's perspective goes down. And when this cost of code review goes down, that incentivizes to reduce the size of the pull request. And this is a reinforcing feedback loop, which is a desired one that we want to have. But that's not the only thing that is going on, right? Why? Because if you reduce the size of the pull request, number of PRs to review in a given unit of time goes up. Okay, if I had a pull request for one pull request per week, and now I halve it, now I have 2 pull requests per week. And also this is multipliable by the number of people in the team, so it grows exponentially. So if number of PRs to review goes up, number of potential interruptions for reviewers goes up. And at one point, it becomes so taxing that the motivation or incentive to review goes down, right? So this balancing feedback loop is pushing against the effect that we want to have. But that's not the only balancing feedback loop that we have here. The other one is also if the time waiting for a review goes up, the temptation, sorry, this is from the previous feedback loop. Okay, balancing. And yes, before I go into the next balancing loop, just for us to notice that there is a conflict here that we have from these two loops. So this is about the motivation or incentive to review, which is pushed in two directions from two sides. Okay, and so if the time waiting for a review goes up, the temptation to start something, start working on something new goes up. We saw it also with Emma. She didn't want to twiddle her thumbs, so she started working on ticket number 3. Okay, and that means that we have even more PRs to review. So this is a reinforcing loop that is reinforcing the balancing one that we have. So it's pushing even more against us. Okay. Okay, so changing gears, let's go into the flow efficiency. So flow efficiency is a metric, again, coming from Lean, and it's pretty simple. We look at the work item, we look at its lead time, and we try to figure out as a percentage of lead time, how much time did we spend effectively working on this item. So Emma coding or Luca reviewing, etc. And the lower the flow efficiency, the worse your process is, and vice versa. Okay. So I started thinking, okay, how can I calculate this and try to represent it? So here on the y-axis, it says average flow efficiency for PRs up to size, but treat it as a flow efficiency, not to go too much into details. And what is interesting to notice is that it starts plummeting at one point. Okay, and you can also understand it is kind of inverse to the wait time per size that we saw, right? And this is interesting because let's do a thought experiment that we have a 300 lines of code change that we need to push through the system of work. And let's say that we can do it in at least 2 ways. So one way, 15 PRs of 20 lines of code. And the other way is 1 PR of 300 lines of code. What this curve is telling us is that the cumulative lead time to push 15 PRs of 20 lines of code through the system of work is going to be way bigger than the cumulative lead time for pushing 1 PR of 300 lines of code. Okay, and this is really important because it means that we are losing throughput as we reduce the size of the pull request, and we work in an async code review manner. Okay, so we have a trade-off. From one side, we have problems with quality. On the other side, the throughput. Now, another way also to understand it is that when we reduce the size of the pull request, that also means that the processing time per size, or the amount of time that we spend working on it, usually goes down linearly, or sometimes exponentially, doesn't matter. But it doesn't go up. But the wait time per size, as we saw, because it goes exponentially up, then the wait time to processing time ratio goes up as well, right? And the way to understand it is that when I'm working on a PR, I'm dependent only on myself. But when I need a review, I'm dependent on other people. And in a system when there's a high utilization and teams that are working individually have a very high utilization rate, the delays start kicking in. And because of that, we have unresponsive system. And because of unresponsive system, the wait time per size goes up. So if you reduce the size of the pull request, the cost of dependencies gets triggered more often, okay? And because of that, we get to see the exponential rise in the costs. And when the wait time to processing time ratio goes up, the flow efficiency goes down and the throughput goes down, okay? Another way to also think about it is that with the promise of the async work is that I can start working on something without the other side being available. And we might think that this is a benefit, but what we're effectively doing when it comes to the economics of the system is that we're reducing the cost of starting work. So the system tilts towards the higher arrival rate, which means we pull even more things into the system, which means that the work in process goes up. As the work in process goes up, we know from Little's law and Kuhn's theory that the cycle times go up and throughput drops. Okay. So when we have high work in process, we have low responsiveness. Because of low responsiveness, we have higher wait time, and when there's a high wait time in the system, lots of delays. The temptation to start working on something else goes up, which feeds back into the wait time, so we have even worse situation. The way that I generalize it, and I think this is a really important point, is that in any system, inventory expands until it matches the delays in the system. Okay. The more delays you have in the system, the more inventory you're going to have. Another thing when it comes to the side effects of async code reviews that I would like to talk about, I'm not sure if you noticed this. Can you review PR, please, in these begging hands? I noticed that people have various ways to beg when it comes to asking for PRs, for PR pull request reviews. And that's the reason why I also say that the amount of begging in the system is proportional to the working process. So what happens is that the more WIP you have in the system, the more of begging you get to see. LGTMs, begging, nitpicking, all of these things are side effects of the way of working. Okay. And when I tweeted it, this one person said they have it so often that they gave it a name and call it merge begging. So if you have these problems in your team, feel free to use this term. So on the bigger PR size of the spectrum, hard to build in quality, or less likely to do so. On the smaller PRs end of the spectrum, the throughput drops. And we need to make this trade-off. So do we lose throughput or we lose quality? Which of these two buttons to press? And for folks that had a chance to read Don Reinerson's book, Principles of Product Development Flow, really, really important book, it reminds me of this batch size optimization U-curve, where we're trying to balance the two costs. In this case, we were talking only about the transaction cost. So if the transaction cost goes up, the optimal batch size moves to the right. Okay. So yeah. And I often hear about this, there's always a trade-off. I know it's a kind of it depends, or there's always a trade-off is kind of consultant thingy. But what I noticed from my career is that there are some trade-offs that actually do not exist because the underlying assumptions are flawed. So we really need to know exactly what we're talking about, what are the assumptions behind what we're saying, in order to understand if there's really a trade-off. And talking about this trade-off and talking about the DORA research and the Accelerate book, which presented its conclusions. By the way, I was thinking about yesterday how to measure the quality of a conference, and the number of citations or quotes from Accelerate book tends to be one of the ways to do so. So NewCrafts is a really great conference. But the biggest myth that it debunked, I think, for us is that it's not either throughput or stability, but it's both of these. So both of these either go up or both of those go down. Okay, so it's not a trade-off. So I'm proposing or saying that that we might have our cake and eat it too. And the way that I try to look at it in terms of what are the things that we can do and what are the intervention points, the way that I see it is that, okay, we have this problem. As the cost of code review goes up exponentially, as we reduce the size of the pull request, the throughput drops. So let's work backwards from there. So we want to have throughput. We want to have small PRs, but we don't want to lose throughput. So let's work backwards. So if throughput, we want to keep the throughput, then we're also saying that the cost of code review per size must not go up. Okay, we have to keep it minimal. In order to do that, the actors' reaction time, where by actors I mean authors and reviewers in this process, their reaction time has to get exponentially quicker and quicker to each other's request. And if we need to have that, then their availability in the system has to go up. Remember, Luca and Emma weren't able to react because they were busy. Okay. So if we look at ticket number 1 here and just pull up its timeline, and let's say that Emma and Luca have this average size of the pull request here, and these are the delays that we get to see. If they want to have a half of that size of a pull request and not to lose the throughput, they would need to react faster. And as we keep reducing the size of the pull request, they have to react faster and faster and faster until they start working together. And this leads me to the conclusion of the study. So the conclusion is that in order to not exponentially lose the throughput while reducing the average size of the pull request, people need to get exponentially closer and closer and closer in time. And that leads us to a continuous code review. Okay. So remember this conflict here that we were having? Okay. That was led from this undesirable side from the number of interruptions. Well, guess what? You cannot get interrupted if you're working on the same thing as the person that is trying to interrupt you, right? And this leads me, is a really good segue to a parallel universe of the pair and mob programming or ensemble programming, or also called software teaming these days, which are jointly called co-creation patterns. How many people here practice these things on a daily basis? Just curious. Cool, thanks. And interesting thing as a side effect of the working in this way is that the way of working guarantees availability of the reviewers. Okay? So what happens when it comes to the economic incentives is that the cost of code review goes to zero. Okay? And what this means in this optimization curve is that the transaction cost drops almost to zero, which means that you can shift the optimal batch size all the way to the left. And then I started thinking, okay, if we tried kind of understanding how would this scatter plot look like in the continuous code reviews, we would have wait time 0 because it's guaranteed by the process itself, right? And the batch size, also the PR size, goes down because when I'm working with someone, they're able to provide feedback in any change that I make, right? It can be as simple as one line of code. And what about the engagement? Engagement usually goes up when the latency reduces, but this is not something that is as important, I would say, in this particular context. At least it doesn't drop. That's what I know. So what are we trying to optimize here for? So we want size to go down. We want wait time per size to go down. We want engagement per size to go up, or at least not to go down. And I try to put that in one metric, so to say, to model this relationship, and I call it PR score. So it's size times wait time in minutes divided by 1 plus engagement. 1 plus engagement because we might have 0 engagement and no one wants to divide by 0, right? So when we think about the continuous code reviews that we get as a byproduct of working together, the size of the pull request can be as low as 1 line of code. And the wait time in minutes is 0, and the engagement goes up or stays constant, doesn't matter. But what is important is that this formula evaluates to 0, and this is actually the best results that we can get. So the way that the formula is also phrased when it comes to optimizing for these dimensions is that the higher this score you have, the worse the process. Okay, if we're optimizing for these things. And that's the reason why I also say that the optimal size of a pull request is the smallest atomic change that is reviewed as it's being typed. And I personally still didn't uncover other ways of doing it besides PRM programming. Okay. So just to give you an example, this is statistics I recently pulled up from one of the teams that I was working with, the XP teams. So they are not only doing more programming by default, there are other XP practices as part of that. But what was interesting to see is that in a time span of 9 hours and 20 minutes, they had 107 commits to trunk. So they're doing trunk-based development, no PRs at all. And the median time to integrate was 2.3 minutes, meaning from start of the change until you saw it on the trunk. And all of these changes were deployable. This is a system that serves millions of customers per day and has a revenue of tens of millions of euros per day. Okay, so it's not a kind of sandbox thingy that we just play or work around, which is a thing that I think my point is that it's possible, right? And it's not that this metric is a goal, this is a byproduct of the way that they work. It's something that we didn't even track. I was just curious at one point to see it. Okay. So, plotting the PRs from the async code reviews, here on the time series, on the y-axis you can see score. And the results were so high that I had to plot it on a log scale. And this is one world that I get to see. And then there's the other world that I see when it comes to continuous code reviews. And this is a really huge difference between these two worlds. So throughput or quality, I would say both. And with that, I would like just to say that we've been told all along that we'll achieve more if we limit and delay our interactions. But I also hope that now you have a data-informed reason not to believe so. And with that, I would like to thank you. I wrote a pretty extensive article on InfoQ last year, half an hour read if you want to dive deeper into this. I also touch on a couple of other topics when it comes to co-creation. And as a byproduct of the study that I did, I also built a tool that you can use in order, if you're interested, how to analyze your pull request. And if you're interested to do that, let me know. So thank you for your time and your attention, and wish you the best of luck. Do we have time for questions, or should we move to the hallway? Yes, time for questions, if there are any questions. Yeah. Yes. So I think the question was if there is a relationship between the number of commits in a PR and with the time for time to get a review. I didn't analyze this part. I guess it's related to the ways that the teams are working, in the sense of how incremental they're able to make the changes. These examples that we saw are not possible if you are not able to make a baby steps and make a very small incremental changes. But that would be interesting. I don't have data. That's the answer to your question. But I would treat it as an interesting hint to understand why these commits cannot land on trunk, right? So there seems to be something that is inhibiting us from pushing these, like even these commits to the trunk. So this batching of the pull requests, because it seems that every of these commits is something that can be merged. I hope so, that they're batched in a single pull request and then reviewed after that. This is kind of a side hint, so to say. Please. Yes. Yes, so that's a really good point. So you cannot do this if you're not doing XP. When I mean XP practices, so it means really good design skills, which enables very fast test suite, right? We also talk about domain boundaries here when it comes to mainstream design, so it also feeds into that. If you have lots of, cross-service things, then you get to have lots of integration tests or whatever you're using to do that, which slows down the test cycle, which then prevents this. But when it comes to this particular team, test-driven development, baby steps, simple design, and working together are the things that are kind of necessary and sufficient to be able to do that. Yes, so all the tests run on every of these commits. Every of these commits were deployable. That's the thing that we want to have. That's the reason why we also push it to trunk. So if I understand correctly, you're saying that in cases where there's a concentrated domain expertise or expertise and the other people are dependent on these people, yes. That's even a more important point to work together because we disseminate the knowledge sooner. And that's why these ways of working help us with that. Otherwise, these people become bottleneck, I would say. So we try to make them as a deliberate bottleneck. This is a term from theory of constraints, so that we can spread the knowledge as soon as possible, disseminate it through the team, so we can enable them to go faster. Okay. Cool. I think we are out of time, so maybe we can move the questions to the hallway. Thanks again for coming, and wish you a nice rest of the conference.